Hello guys, in this video I will talk about the midterm exam. So today I'm Vinji recording and Vinji grading everything I have delayed so far. So I have graded your exams, your exam answers. Yeah, okay, let me explain what I wanted to what I wanted in your answers and yes, and the correct answer. So let me tell you this: homework is repeated every year. Still, there are errors. Still there are errors, uh, not caught over many years. But in the exams, I make the questions every year. I make new questions every year. So sometimes I am not good at. I didn't do a good job asking in a correct way. I have to ask well for you to answer well. So in this midterm exam, question one is I think I did not do a good job in asking a question. So let me just show you what I wanted. First of all, it is pretty simple. Basically, even though I wrote a lot, but in the end, this is what you get. And two regressors with an intercept linear regression, pretty standard. And so then in that case, you can think about like this this model, right? So you can think about this regressor here, and the full rank assumption is rank of expectation xi time is 3 in this case, because x is 3 3 by 1 factor, and this is that. But in the end, I think we have done this earlier in another homework or in somewhere. We know that the full rank assumption is variance of x1 is not 0, and variance of x2 is not 0, and finally correlation is not plus minus 1, right? So these are three assumptions. The first assumption is obviously the first assumption is about the variation in x1. Second assumption is about the variation in x2. Third assumption is about multicollinearity. There is no multicollinearity when correlation is not perfect. Or you may interpret the first assumption as by the first one, you can guarantee that x1 is not multicollinear with the constant. So x1 is not a constant by the first one, okay? So anyhow, there are three different pairs of possible multicollinearity, and they are ruled out by these three assumptions. By the way, this is true only when you have two regressors. When you have more than two regressors, the condition is not as simple as this. Okay. So, or anyhow, you can take this, or you can think about determinant. You can calculate determinant and show that is not 0. Okay, that is possible. Then let me see what was the question. Full rank assumption, necessary and sufficient conditions for the regression's full rank conditions. What I wanted is I want you to interpret these three conditions back to those three actual variables like G, I, R, right? And in terms of G, R, I, variance of x1i becomes variance of GI minus inflation not equal to 0. But this variance G minus I is variance of G plus variance of I minus 2 times covariance. This is the condition, okay? And the second assumption is variance of x2 is variance Ri minus, which is variance R. Okay, I didn't know why. This is not 0. And the third assumption, correlation. By the way, the correlation different from plus minus 1 can be interpreted as like and the last condition is equivalent to the variance, multiplication of the variance is different from covariance squared. That is equivalent. If you think about the definition of correlation, it'll be easy, right? So if you square the correlation, then you will get that. And then in this setup, the covariance times variance x2i minus covariance x1 x2i squared can be written as, this is also annoying. So you replace variance x1 with this guy and covariance x2 with this guy and covariance with something more complicated. So, and rearrange those things, and you can express them in terms of those things, right? That's what I meant. But if you can up to here, that'll be okay. That'll be fine. Okay, so and here I would like to say a few comments. First, independence. First, let's think about this. Identification and sample size. I have been repeating this many times. Identification argument, when I say, can you identify something or not? That means when you have infinite number of samples, can you estimate it correctly? Something like this, okay? So sample size, finite sample does not exist in identification argument, right? Here, this variance or this kind of expectation, correlation, variance are true population expectations, right? True expectation is if you know the true distribution, which means if you have infinite samples. But finite sample mean is, so the true expectation is population mean. Sample mean is different thing. So if you only have finite observations, that is key difference. So because sample mean could be different from the true mean. Always keep that in mind. That means even if say Rx is not 0, true mean could be 0, right? So sample mean not equal to 0 does not imply the true mean is 0 or not, right? And in your argument, you have to use true population expectation everywhere. And second comment, independence. Independence, uncorrelatedness, and like a linear independence. So there are different notions of independence in different fields of like mathematics, statistics. Okay. First, statistical independence means that it's literally full independence, very strong independence. That means the probability of x and y can be split into probability of x and probability of y, like this, right? So you may think this is actually this is really strong independence assumption. Uncorrelatedness means that xy is expectation x times expectation y. So it only allows expectation, right? To see the difference under statistical inference, what you get is you get this. So when x and y are fully independent, then expectation of a function of x and another function of y can be split into expectation of gx times expectation of hy. So no matter what this function is, you can split the expectation. This is possible in full independence, but when I say uncorrelated, then you do not have a function here. The g, you cannot allow any function there. You only have like linear functions here, like x itself. This is much kind of weaker. So whenever x and y are independent, they are always uncorrelated. But the converse does not hold in general. Okay, that is a problem. And linear independence is not a statistical term. It is a linear algebra term, so it does not think about randomness. But linear independence between two random vectors means that there exists a non-zero constant such that like probability x equals say c times y is 100%. So x and y should move perfectly together with 100%. So it is a really strong independence assumption. Linear dependence. Linear independence is the negation of this. If this kind of constant c does not exist, then they are linearly independent. Okay. And then another thing here is now let's think about independence, simply statistical independence. You may think independence between x1 and x2, right? So like here x1 and x2 can be linearly independent, can be statistically independent. That is possible. But also at the same time, I and xj, or you can think about independence between first like xi and xj, right? So you observe two people, and the first person and the second person are independent. That is another independence. So we are looking at different dimensions, right? Independence between a variable from another, but here it is an independence of an observation from another observation. So the second independence is IID. This is IID assumption. Follows from the IID assumption. So if you throw a coin like repeatedly, then the first throw is nothing has nothing to do with the second throw. So that is IID. But like your coin toss has nothing to do with your midterm exam score, right? Even if you are really good at throwing a dice, that does not improve that has no correlation with your econometrics score. So that means two different variables independence. Here, this covariance, of course, in this argument, everything is across variables, not across observations, right? So it can be confusing. So please think about what you are talking about. So, and the second question was pretty easy and everyone did it correctly, I think reasonably well. So I will skip that. So what I want to say here is, the main point here is, even if those covariances are not exactly zero, that doesn't mean there is a problem. So each variable, like a G or I, may be correlated with error, but the actual variable you use in the regression is not a G itself, but G minus I. So the correlation could be cancelled out. That is possible, right? So very minor tweak. And another question, actually, when I think about this question, another idea of mine when I make the exam, I wanted to think about this. Like, so y is, like say alpha 0. So y is alpha 0 plus beta 0 gi minus ii plus gamma 0 ri minus ii plus, say now, delta 0 ii plus various epsilon plus epsilon. I thought about like making a question like this. So you have real, what is that? Real growth, and this is real treasury rate, and this is inflation rate, right? But inflation has been used here and here. We have already used inflation there. So can we identify this model? Regression. I thought about this question. But I thought it could be too difficult. But now I think you can handle this. So think about this, just without trying this. Guess if it is identified or not, right? The answer is yes, it is identifiable. We can identify this even if already inflation is used to calculate real rate. That causes correlation, but that does not block the identification. It's not a big problem, because in other words, you may think like that. So think about this. So if you think about this simpler model, I just include G, R, I separately, then you will agree that this will be identified. So, of course, as long as G, R, I, and the intercept are not multicollinear, under the standard full rank condition, this regression is identified. And then, as long as this is identified, you can identify this, because rewrite the second equation like this. So the first equation to, so here beta 0g, so I will expand the I terms. That means right? So if you like the first equation is converted into here just by expanding these two parentheses, and then beta tilde is beta 0, gamma tilde is gamma 0. The only difference is delta tilde and delta 0, right? But if you can identify alpha, beta, gamma, delta from this equation, you can recover those alpha 0, beta 0, gamma 0, delta 0. If you identify like tildes, let's say tildes, then you can identify the original parameters. It's like reduced form and structural parameter. Because obviously beta 0 and gamma 0 are identified because like beta 0 equals delta beta, so gamma 0 equals tilde gamma, and we wanted to identify delta 0, that is easily tilde delta plus tilde beta plus tilde gamma. So in this way, this equation is still identified. Okay. So it may look like it's not identifiable, but actually it is. That's what I wanted to say in this question. Okay. I will continue to question 2 in the next video.